Hi, AP Calculus students. How you doing? This is it's New Year's Eve. This is what you do when you're a math teacher on New Year's Eve. So it's my first video in a while. So I hope I do a good job for you. So I am really excited though. I hope you are too. This is the introduction to chapter 4 on integration and antiderivatives. So you are basically starting the second half of calculus. It will be, not that there aren't some hard parts, but it'll actually be easier because this is antiderivatives. So we're just doing derivatives backwards, and you already know what derivatives are. So you already have a lot of calculus concepts under your belt. And so switching to antiderivatives, the inverse of derivatives, will be easier for you, right? Because you know the underlying function. So you are welcome to take notes here. I would actually prefer that you don't. I would prefer that you just watch this twice, instead of just to get a feel for what chapter 4 is about. Okay, so what I made myself some notes here. So second half of calculus. Now, what we learned is limits, derivatives, and now antiderivatives, which is called integration. We will be using integral signs, okay? A new operation that you've never learned before. Now, what we learned is that derivatives were based on limits. A derivative is the slope at one point, or the slope of a tangent line, or an instantaneous rate of change, right? And this was its symbol, among other things, right? And it's the slope of a tangent line, and its meaning, like I said, is an instant rate of change. And the way it was related to a limit was if you had 2 points to make a slope, it was the limit as the distance between those 2 points approached 0. So how are limits related to integration? Well, it's really cool. Obviously they are if it's the inverse, right? And so it's already based on derivatives. But an antiderivative has this elongated S sign. So it's an S, but it's elongated. And geometrically, when we looked at derivatives, we drew it as the slope of a tangent line, right? What an antiderivative is geometrically is an area. So when we look at a graph now and they ask us about an antiderivative, we're going to be looking at the area between the function that is graphed and the x-axis. So that's how it shows up. What does it mean? An integral or an antiderivative is accumulation. So for a derivative, an instantaneous rate of change, very important, right? For things that are moving, especially very fast, what at that one moment is the rate of change? Accumulation is an antiderivative. And imagine how important that is, because that's kind of what we base our life on, is accumulating, right? How much money do I accumulate? How much oil is accumulating, maybe if we have a spill on a lake, something like that. And then good things that we like to accumulate also, right? So I'm going to be proving by the end, kind of proving that, well, how does that happen? Why is it an area, and why does it represent accumulation? Okay, so let's go to our first example, right? So a teacher is walking to raise money for charity. The teacher walks 4 miles per hour for 6 hours. How far did the teacher walk in 6 hours? Obviously, this is very easy for you, right? The teacher is walking 4 miles per hour. They do that for 6 hours. Obviously, they've made it 24 miles, right? So 24 miles, and we'll just circle this here. All right. How do we show that algebraically? We know distance equals rate times time, right? So what we had, our rate was 4 miles per hour, and we multiplied that by the time, which was 6 hours. And we knew by dimensional analysis that the hours canceled and actually left us with the correct units, miles, right? And 4 times 6, right? So we've done this since probably pre-algebra, maybe before. Okay, so let's make a graph of that. So here's hours, and you're so used to distance being on the y-axis is not. We're going to graph the rate, right? And so notice that the rate stayed at 4 miles per hour. So it's just constant for the 6 hours. So how would I get from this picture how would I answer my question? How far did this teacher walk in 6 hours? We said that's 24, right? Which was 4 times 6. So in other words, it's the area of this rectangle, right? Base times height, right, is 6 times 4 is 24, right? So algebraically, geometrically. Now, let's talk about what you're going to learn in chapter 4, integration. What if this is the integral sign. What if we integrated the function 4? There it is. You may wonder, what is this dx? We'll get into that more later. But here's the idea. Why we need the differential of x right here. It goes with the integral sign. So when we perform the operation, the integral sign and the differential, the derivative of x also disappears. They're a pair. And here's why. So here's the question with an antiderivative or integration is, what function, when I take the derivative of it, because it's the inverse, gets me 4? Right? I'm reversing. What function, when I take the derivative of it, gives me 4? Well, that would be 4x, right? If I took the derivative of 4x, I would get 4, right? So working backwards. Now, hopefully you can see why I needed this differential of x here, because I wanted to write 4 times a variable, but how did I know what variable to use? Sure, we use x all the time, but wouldn't the derivative of 4t be 4, right? So I kind of needed this to say, what variable am I going to put here? So take a look here. I did the antiderivative, right? And notice I got 4x, and notice if I evaluate that at 6, I also get the 24 miles per hour that I see in the area and with the algebra. So again, what I'm trying to bring to your mind here is that an antiderivative can be represented as an area, okay? The other idea that I'm trying to bring to your mind here is that notice when I took the antiderivative, the integral of the rate, it gave me a distance, right? When I evaluated it at 6 hours, it gave me a distance. So that is another indication that an integral is the inverse of a derivative. Because let's look over here. If I take the derivative of a position or a distance function and I get the rate, then notice then if I integrated the rate and it gave me a position, that this is an indication they are inverses of each other. And again, what I'm trying to show is that an integral geometrically is represented by area. So, and these are inverses. Okay, let's see if that holds true for this more complicated problem. It doesn't seem complicated, but it's kind of interesting that it is complicated. And I'll show you what I mean. Okay, I better come on this side so you can see my writing. Let's see if I can just give you a little bit more room there. You're on your bike and it is starting to rain. So you increase your speed. Your speed is y. And the function for your speed is 2 times x. So you are doubling your speed. This is in meters per minute. And you are doubling your speed every minute. You're like, I am going to get rained on. Okay. So how far have you gone in 6 minutes? Well, you haven't gone 2 times 6, 12, right? Because at the beginning, right? This is your rate function here, right? So at a time of 0, you were going 0. At a time of 1, you were going 2 meters per minute. At 2 minutes, you were going 4 meters per minute. At the end, you were going 12 meters per minute. But that was just at the end, right? So the question is how far did you get when your rate, how your speed was changing? Even though it was changing constantly, isn't that kind of weird that we can't really say how fast you were going just because it wasn't constant the whole time? It was just constantly changing. So how do we figure this out? Well, how far have you gone in 6 minutes is the idea. Can we do distance equals rate times time? I'm not sure because, at the end, I was going, 12 meters per minute, but not at the beginning. So the rate was changing. So I don't think, right now, I don't feel comfortable doing distance equals rate times time because the rate was changing. So let's go to area. Let's see if we can help ourselves. Okay, let's graph the function. Super easy to graph, right? The minutes are on the x-axis and the meters per minute are on the y-axis. Okay, so that means at 1, I was going 2, right, 4, and I really could just, draw my line here, right? So there we go. All right, and so I graphed the function y equals 2x here. All right, now let's see what I can do to help myself with distance equals rate times time. Let's make ourselves a chart since our rate is changing and x is going to be the time in minutes. And let's first do the area, then the distance, and then let's do the integral, the antiderivative. Okay. So let's first do the area. Well, I know how to find the area of a triangle, right? That is 1/2 the base times the height. All right, let's see. Let's get that area. So let's just progress along, right? Let's do this little triangle. Well, that is a base of 1, a height of 2, and 1/2 of that is 1. Okay, let's go a little farther. Let's do this bigger triangle right here. Base of 2, height of 4, that's 8, 1/2 of that is 4. Let's go to a base of 3. Base of 3, height of 6, my drawing's a little off, right? That's 18, 1/2 of that is 9, right? When I go to 4, right, that would be 4, right? And then 1/2 of that is 4. So that would be 16. Let's see, 5, height of 10, bad drawing, right? There we go. That's 50, 1/2 of that is 25. And then last, that'll look a little bit better. I guess I was a little off. So base of 6, height of 12, right? And 1/2 of that, so that would be 36. Okay, so there's the area, because I felt that these were all related, so I just did the area first. Okay, now let's do the distance now. Let's just do that for 1 minute. Now that we have a chart to help us, let's take a look. For 1 minute, at the beginning of your first minute, you were going 0, right? At the end of your first minute, you were going 2 miles per hour. And because you were constantly changing, I think we can use the average rate, can't we? So let's do distance equals rate times time now. Now that I can see what's going on. So for the first minute, I was going 0 at the beginning, 2 meters per minute at the end. That average is 1. I was going 1 meter per minute for 1 minute. 1 times 1, I think my distance was 1 meter. Okay, not very fast at all. Okay, let's go to 2. Okay, so how far did you go from 0 to 2 minutes? So from 0 to 2, let's see, I did that for 2 minutes. My rate was 0 at the beginning, 4 at the end. The average is 2. 2 times 2 is 4. How far did you go in 3 minutes? There's 3 minutes. Okay, let's see, 0 at the beginning, 6 at the end. The average is 3. So for 3 minutes, your average was 3 meters per minute, 9. 4 minutes, at 4, you were going from 0 to 8, half of that is 4, rate times time. Your average rate was 4 meters per minute, and you did that for 4 minutes, 16. So you can see a pattern here. Kind of interesting, isn't it? There we go. 5 for 5 minutes, 0 to 5, you were going 10 at the end, 0 at the beginning, average of 5, rate times time. There we go. And of course, we'll get the same thing, the same pattern for 6, right? Isn't that kind of interesting? All right. Now, let's go to integration. What happens if I integrate or take the antiderivative of the rate function, right? So in other words, I am looking for a function that when I take the derivative of it, I get 2x. That would be x squared, right? That would be x squared. Right, so think about that. When you take the derivative of x squared, you do in fact get a 2x, right? And when I integrated, this was a pair, they did cancel. All right, let's evaluate x squared at the different x's that we have, right? So here we go, let's fill in this row. X squared is the integration of 2x. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and 6 squared is 36. Isn't that cool? So do you believe me now? Do you believe that when you integrate a rate that you get a position or distance, and so it must be the inverse of a derivative, because when you take the derivative of a position or a distance, you get the rate. Do you believe me? Do you believe me that if you graph a rate function and they ask you what is the integral, what is the area, that it is the area between the rate function and the x-axis? Do you believe me that it represents accumulation? Isn't that what happened? When I had a rate here and I integrated, right, and drew its geometric representation, when I had a rate, it gave me how much distance I accumulated, right? When I had a rate here, it gave me how much distance I accumulated, okay? And so this is what we are going to be working on in chapter 4. And I find it fascinating. I find it useful. And I hope you do too.